Hello, today we're doing 8.4, testing the difference between proportions. SWABAT is going to be to perform a two-sample z-test for the difference between two population proportions, P1 and P2. Two-sample z-test for proportions. These are going to be used when the difference of two population proportions, P1 and P2. Three different conditions need to be satisfied in order for us to do this. Number one, the samples have to be randomly selected. Number two, the samples must be independent. And then number three, the samples must be large enough to use the normal sampling distribution. So what that means is these 1, 2, 3, 4 things have to be in place. We'll talk a little bit more about those when we get to it. Next, you got a lot of formulas that we're going to look at here. I'm going to have you kind of just go through them, read them a bit, and scan them. I'll tell you the one that we probably will use the most and that you should probably highlight include the one for the z-score, because we're going to need those and we'll need to compute them. Pretend like that's highlighted really well and not scribbled. And then the other one that you need to note, at least, or the other thing that I would note from this, is each one of these products has to be greater than or equal to 5. Kind of stated that earlier, and we'll use it in a bit to make sure that you're okay with it. Next thing, similar chart to what you've seen before. We'll have to do some verification, and then some formulas that you would want to know is this one for sure, and then this is normal, we've done this. And then if you haven't grabbed your Z chart, you want to go ahead and do that. That's table 4, your Z chart, because you'll need it for this lesson, sort of. And then this formula. Again, these are the main things that you're going to need in order to do this, and then we'll follow these steps. Not a lot of calculator stuff in terms of it doing the work for us, but there are some things that you're going to want to know. So if you don't have your z-score, I guess it's not a big deal because I put this chart on here, and this will kind of help us out. When I give you a problem, you're going to look at this with regards to the alpha. So not really level of confidence, but more so level of significance. And with the level of significance, which we call alpha, so if it's 90%, then for this one, your alpha would be 0.1. For this one, your alpha would be 0.05. And for this one, your alpha would be 0.01. So some key things, kind of, it's going to be a nice little time saver for you all if you have it. So example 1. Let's determine whether a normal sampling distribution can be used. If it can be used, we're going to test the claim about the difference between proportions, P1 and P2, at the given level of significance alpha. We're going to assume that the samples are random and independent, mostly because they kind of have to be. So the first thing I want to do is determine if I can use this. So in order for me to be able to use the correct sampling, a couple things need to happen. So number one, N1 times P bar has to be greater than or equal to 5. And then N1 times Q bar has to be greater than or equal to 5. This is, where am I getting this? Let's just remember from right here. All of these have to be greater than or equal to 5. We also said it right here. So this is what we're going to test. And in a moment, we'll plug in the things to know for sure if we got it. So let's fill this in a little bit more. So what else? I just lost it. N2 times P has to be greater than or equal to 5. And then N2 times Q also has to be greater than or equal to 5. Okay, so the N's are kind of nice and user-friendly because I can see them just by looking at the equations. Like here's N1 and here's my N2. What I don't have is the P. Now there is a formula for this one. Pretty sure I didn't have you highlighted, but it's probably something that you should do. So if you go back to that page, this is pretty crucial, kind of a necessity. So highlight this, also memorize it. The P bar is equal to x1 plus x2, so it's like the total of the x's divided by the total of the number of things that you collected. The Q, kind of easier, you just do 1 minus that because it's the opposite. So if P bar was 60%, Q bar would be 40 because they have to equal 100. So let's check out and find out what our P and our Q bars are for this example. So for P bar, I'm going to kind of just try to squeeze it in here. that's going to equal, we said it was the total, so the x1 plus the x2, so here's my x1, 471, plus x2, 372, divided by the number in the sample, so 785 plus 465. And then if you have your calculator, you can add the numerators and the denominators and divide, and you'll get 0.674 and some other numbers. I'm going to go ahead and round off at about, well, I'll give it 3 decimal points. Let's keep it a little bit more accurate. 674. So if that's the P, then the Q is just going to be 1 minus that. So 1 minus 0.674, which is 0.326. So this is verification. So in order to verify, I'm going to multiply N1, which is 785, times the P-bar, which is 0.674. When I multiply that, I do get 529, which is definitely greater than 5, so it kind of passes that test. You're going to do the same exact thing, but you're going to plug in the other values that you have instead. So, a little technical difficulties here. You can go ahead and press pause and do this. I'm kind of just going to fill it in really quickly so that you can see it, but this would be in 1, so that's 785 times the Q, which is 0.326. Is that greater than or equal to 5? It is. It's a big number. It's 256 about. So definitely greater than or equal to 5. Then you do the same thing for N2. Your N2 was 465. And then that times the P would be 0.674. That also is greater than 5. If you think about it, it's like 67% of 400. It's a big number. Definitely bigger than 5. And then for your last one, you're multiplying N2, which is 465, times the Q bar, which is 0.326. And then if you multiply those, you also get a number that is definitely greater than or equal to 5. So all of the things that it needed to satisfy, it does satisfy, so that means that we can proceed with a normal sampling. So in order for me to do this next part then, because now I want to test the claim. The claim is that P1 is less than or equal to P2. So let's talk about that in terms of my hypothesis. For this, thinking about the alternative and the null, this is a null hypothesis. It's saying that P1 is less than P2. So the null part of that one is going to be P1 is greater than or equal to P2. And we're going to assume that the null is true. That means that they could be equal to each other. So what are my what's my critical values here? Well, here is this, and because this is pointing to the left for the alternative, it's going to be a left test, which is great because it means my variable to the left. And then if we look at the alpha for this, it's 0.05. And then if you go back to your shortcuts right here, for 0.05, it should be 1.96 for my critical value. 1.96. Area to the left. So this is my rejection, and if it's on the left side, it's going to be a negative value. So negative 1.96. And now I need to find that wonderful critical Z. So your formula for your critical value Z is given up top. You highlighted it a couple times, but I've just written it here so that we can kind of see what we're getting and where we're plugging it into. Let's find out some things. I need to know what the P hat is, P1. So we had a formula, P hat for 1 is equal to X1 over N1. So what that means for us is, well, our X1 is 471 divided by N1, which is 785. And so when I divide that, I get 0.6 about. Shoot. Minus P hat for the second one is going to be X2 divided by N2. So X2, 372 divided by 465. When I divide that in my calculator, I get 0.8. Minus, now P1 minus P2. Remember, we're assuming that the null hypothesis is true, that means that we're assuming that they could be equal to here. So if these are equal to each other, if I subtract them, I should just get 0. It's going to be kind of an always 0 type of a thing. Then the square root, p times q, or p bar times q bar. And so what am I multiplying there? Those numbers that we just found out, which is 0.674 times 0. These are these values right here, 326 times the square root of 1 over n1, and we know that our n1 is 785, plus 1 over n2, which is 465. All of this I'm going to do in my calculator. The main thing here, the only thing I would simplify first is probably this part, and then just do negative 0.2 divided by all of this. It's all, for me, kind of easier to just do in a calculator. So I get a really, really small z value at negative 7.29. Check it on your calculators. Make sure you get the same thing. And so this is way, way, way over here. Definitely in the rejection area. So I'm going to reject the null hypothesis. So if I'm rejecting the null hypothesis, my claim was an alternative. That means I'm going to be supporting the claim. There we go. Okay, do us a favor. This video's try this one on your own. Try it and see how you do. Press pause and then unpause when you're done. Okay, so my p bar is 6 plus 4 over 20 plus 30, which is 10 over 50, which gives me 0.2. My q bar is 1 minus the p bar. That's 0.8. So for the first setup that I tried, n1 times p bar, it's 20 times 0.2. That has to be greater than or equal to 5. Well, 20 times 0.2 is 4. Not greater than or equal to 5. Therefore, we cannot use sampling for this example. That is part 1 of this lesson, and then we will work out a complete problem in your next video.